So let's go to the last part of the lectures. So I divided approximate verification into 3 areas. First area, interactive proofs. So there a verifier interact and use random coins. Okay? Now second model, PCP. So you kill the interaction, the prover has to provide a proof, but the verifier only sample the proofs. Okay? And the third model, which we do now, is we forget about the proof, we just want to sample the data, okay, and we want to verify something approximately, but this time we introduce a distance. Okay, and the key notion of an epsilon tester is that we fix an epsilon, and then we are searching for a randomized algorithm such that, so I'm talking about an epsilon tester for language L. So if X is in L, the algorithm always accepts. Okay, if X is epsilon far from L, epsilon far from L. So this is of course a weakness. We weaken the not being in L. You know, the only thing we want to guarantee, if we are far from L, then we should reject with high probability. So either, if you want to stick to the notation we had there, you could say that we won't accept with more than probability 1/2. But usually people write it like this, is that we reject with high probability and we accept with high probability in this case. Okay? And in this case you have a two-sided, people call this a two-sided tester. Here they would call a one-sided tester. A one-sided tester follows exactly the same definition as the interactive proof and the PCP. You know, if you want to generalize it, you talk about the two-sided tester, but most of what we do, actually we have a one-sided tester. Okay, so the key ingredient now is we have a distance on objects. So I gave you an example of graphs with the edit distance on graphs. Okay, now we talk about words and trees, and we stick to very classical problems and see what we can do with this. So first thing is, what are the distances on words and tree? Okay, so obviously people talk about Hamming distance, and Hamming distance, generalized Hamming distance in the sense that even if the words are not of the same length, you fill them up so that they have the same length. And we've seen that the edit distance is actually smaller than the Hamming distance, and the edit distance with move is actually smaller than the edit distance. Okay? All right. Now, if you see this definition, and you imagine, let's suppose you have a tester for the Hamming distance. Question, would you get a tester for the edit distance? Okay? And you can of course play conversely. Suppose you have an edit tester, an epsilon tester for the edit distance. Do you have a tester for the Hamming distance? Okay? More generally, suppose the property is testable for the Hamming distance. Is it testable for the edit distance? Okay? That's a typical big question. Now, believe it or not, it's an open question. Okay? So what is clear is that suppose you have a Hamming distance tester, you will have an edit distance tester. Why? Well, let's suppose the words are far for the edit distance. It means they are far for the Hamming distance. Therefore, I use the Hamming tester and I'm in business. But nobody knows. So every time you have a tester for Hamming, you have a tester for edit. Nobody knows if the converse is true. Okay, it's actually very challenging questions. And people believe, okay, so it depends of course on the structures, because here we're talking about words and trees at the same time. It could very well be that on words and trees the situation differs. Again, you can of course play the same game with this, okay, but here we know the answer. I will show you an example that something has a tester for the edit with moves, it doesn't have a tester for this. Okay, so I know the answer here, I don't know the answer there. And of course, this will be related to non-deterministic property testing, as we'll see in a minute. So in this area, there is a big, challenge. Is that called the T. T would be the properties that are testable deterministically. So in that sense, and then we're going to introduce properties that are non-deterministically testable, and the fundamental thing is whether T equals NT, which is of course equivalent version of P equals NP, but here in this world being efficient doesn't mean to be polynomially computable, it means being testable. Okay, and it makes totally sense for big data. Okay, big data, you can't read them, it's too long, but you can sample them. So, and the whole question about testability is what can you do with assuming you can sample the data. Okay? So we'll see some answer for that, but in many cases this is an open question. So there are plenty of things that are quite open. The notion of non-deterministic property testing was introduced by Lovash about 2 years ago. So here we're closing to recent research. And actually what he did is that he introduced it in the context of graphs, and actually in the context of dense graphs. Okay? And he showed that for dense graphs, T equals NT. Okay? And then he showed that for sparse graphs, T is different from NT. Okay? So this is, his paper is, if you put non-deterministic property testing on Google, I'm sure the first paper you'll find is the Lovash paper. Now, as you know, Lovash is an extremely influential computer scientist, I should say mathematician, and but he introduced many ideas, and I think this is also one of them, but very recently introduced. Okay, so we'll come to this in a minute, and so first of all, how artificial is this distance? So we've seen that this is quite natural. Of course, this is classical. Now, how artificial or how natural is the edit distance with moves? Okay, take the example of a tree. Okay, so you have the basic structure that people use in computer science is an ordered n-rank tree. Okay, so ordered means you have a first successor, second successor, third successor for this node. Okay, and you edit by removing edges or adding edges, and the move is moving, for example, this subtree there. Okay, that's equivalent of a move in one. So the cost is 1. So the cost of an edit is exactly the cost of a move. All right, but just imagine, think of the tree as a graph. Okay, if you think of the tree as a graph, then you can remove this edge and add this one. Okay, so if you think of the tree as a graph, the edit distance with move is actually the edit distance on graph. Okay, so that's something which is helpful to figure out, is that the edit distance with move is not that artificial. It's something that is pretty much looking at trees as graphs. Okay, and in some ways you could look at words as graph. Okay, because what is a word? A word is nothing than a linear order. Okay, where you put here labels. Okay, this is a word. Now, if you think of a word as a graph, and you remove an edge and you add an edge, you have a move. So it's exactly the situation. Okay, so it's actually useful to think of words as logical structure. And typically, when you look at a word as a logical structure, so you're given a domain, usually you're given a unary notation to specify where do you get a B. Okay, and then you assume that if you don't get a B, you get an A. Okay, maybe you've seen this before. So you have unary predicates that specify the labeling. So you may have several. And then you have a successor relation that I wrote here. And then you may have an ordering. So the ordering is a transitive closure of the successor relation. So for example, if you add it as a graph, you have to add all the edges here. Okay, this is the ordering. Okay, usually people figure out, well, as a logical structure, if you have the successor, of course I can get the ordering, and if you have the ordering, you have the successor. Okay, but the reason I take it like this is for a good reason. So now, if you think of a finite structure with some unary predicate and binary predicates, okay, this is what you have. So in some cases, you treat the binary predicate as a graph. So you have actually two binary relations that are graphs. But look what happened. This is a sparse graph, and this is a dense graph, right? So therefore, if you want to look at a random object, what is a random? Substructure. Well, random substructure is that you take of course random points, okay, but then you apply the model of graph. So if the binary relation is sparse, you take neighborhoods, and if the binary relation is dense, you take the induced subgraphs. Okay, so it means the following: that if you have this is a word. Okay, so here's the random point, say I. Okay, and let's suppose I have another one, J. Okay, so what should be my substructure relativized to I and J? Well, for the successor, I look at distance K on the successor. Same here. But then I'm going to take the fact that this segment is before that segment. I will take the ordering between the two. Okay? Now you can imagine if you look at a word as a successor only without the ordering, then you get samples as subwords, but you don't know which one is before which one. Okay? Which is of course another model. Okay? Now, as we have seen yesterday, I want to take higher order statistics, and obviously which one is before which one is the key. Okay, if you don't take this, you're missing something. Okay, so now on trees. So remember yesterday we introduced this statistical notion. So let's erase this. So first thing we introduce is the stat. So U stat sub k over word W. Now, and this is a density vector. Okay, so here you have a vector of size 2 to the k if you're on a binary alphabet. Okay, and the component on U sub I is either you interpret it as a distribution, so it's a probability if you take a random position to see U sub I, or you interpret it as a number of occurrences divided by the number of global occurrences. Okay, it's the same thing. And then we introduce, say, U stat square, which U stat square is exactly the same thing, except instead of having one, so now the dimension will be 2 to the k by 2 to the k, and then each component is actually a pair U sub v, and you interpret it as what is the probability to see U followed by v when I take two random samples. Okay, and we had an example where I computed exactly the distribution, but you can think that on a huge word, this is of course something extremely important to figure out, and then of course you generalize it to some p, So if you want, now you have component user 1, user P. Okay, so now the dimension is 2k to the P. And now you interpret it as I see U1 followed by U2, followed by UP. And of course, every time P increases, it gives you better and better approximation of what the word is like. Okay? Now, this you can do with trees. Okay? It's less obvious. So how do you do? So remember, when you have unranked trees, it means here the degree is unbounded. Okay? So what is a U-stat vector on a tree? So the U-stat vector, say first of all the U-stat k of a tree T with n nodes. What is it? Okay. Well, there are two ways to do it. One way is to binarize an n-ranked tree. There is a way to rewrite this as a binary tree. So maybe you've seen this, maybe you don't. Let's do a simple. I don't want to make it too difficult. So let's take a tree like this: A, B, A, B, A, B. Okay. I'm going to binarize it, so you see what's going on. So when you binarize it, you essentially have a left successor now and a right successor, which is not an ordered tree anymore, because you may have a right successor without a left successor, as we're going to see. And every time you go down, you go left, and every time you go horizontal, you go right. So for example, here I would go left, because on this B, okay, and then this A and this B would be a right. Like this. Then I go left, this A is here, and then this A and this B is this. Okay. The equivalent, the interesting thing about this operation is that it doesn't change the cardinality of the tree. Okay, you still have the same domain. Now you have left and right successors, and you see this point, for example, it has a right successor but it doesn't have a left successor. So it's not an ordered tree, but it's some kind of generalized binary tree. And then what you can do is, if you take a random point, okay, you can look at essentially the subtree at depth k. Okay, so let's suppose k equals 2. Then see, if I take this is my random choice, then the tree I see is exactly this one. Okay? But because I have a binary tree, at constant depth, I have finally many possibilities. Okay? 2 to the 2k, for example. Okay? So you can keep density vectors over 2 to the 2k possibilities. Okay, which is, of course, the dimension is going to be much larger, but still finite, okay, for a tree. All right? Now, what is a U-stat square? So U-stat square is more interesting, is that when you have a large tree, and imagine, so you have to think of a large tree. So people, in these XML communities, in databases, the fundamental problems, and all rely on this framework. But so you take two samples. Okay, let's take this sample, and maybe the other sample is here, or maybe it could be here. So if it's here, it means it's a subtree, and otherwise it's here, it means there is a common ancestor here. Okay, so there are two possibilities on a tree if you take two random samples. Either they are totally, they are not in the ordering relation of the tree, but they have a common ancestor, it could be the root, or one is before the other. Okay, these are the two cases. Okay, so you can imagine that now, instead of having, now you have two components, say T1, T2, and then you put 0, 1 to indicate, well, this is, well, let's write it like see. Well, let's leave 0 and 1. So that would be the 0 situation, and that would be the 1 situation. But in the 1 situation, okay, what is important that is this guy is before this guy. In which ordering? Usually, when you have an ordered tree, you imagine that you go on the depth first, run, which is usually it's called linearization in an XML. So you're going to see this tree before that tree. Okay, which is important, right? Because you'll know this. If you take this sample, you know that you've seen T1 before you have seen T2. All right. Now, if you have 3 samples or 17 samples, you can also build. You start to the 17 on trees, but then you have to cope with all possibilities of the subtrees, which is totally feasible because it's finite, but now of course it's going to be huge. Okay, and once you do this, then you have exactly what you need to proceed. Okay, so let's now. So what we did yesterday was to discuss the equality of 2 strings. Okay, so you remember when you have equality on 2 strings for the edit distance with move, we want to decide is W equal W prime. Okay, you have 2 words. They should be approximately of the same length. Okay, and what you have to decide is, are they exactly identical? Which would be, here the pair W prime is in the equality language, or they are far away, far apart for the edit distance with moves. Okay, we only do this. Okay, and then the way to do it, very simple. First you sample W and W prime on the same random position, so you get some U-stat W for some variable k, for some k. So here k is taken as 1 over epsilon. Okay, so this is going to be the randomized version of the U-stat, and we have seen that it is close for the L1 distance to the U-stat. Okay, then we do the same thing for U-stat prime for the W prime, and then we look at, is it smaller than epsilon or not? Okay, so our tester is exactly like this. We take random samples, we build this vector, which is the U-stat vector on the samples. Okay, how many samples? 1 over epsilon square. We do the same for U-stat W prime, and we take the L1 distance between these 2 things. Okay, if it's smaller than epsilon, we accept, and if it's bigger than epsilon, we reject. That's it. Okay, so what we proved is that, of course, if the words are identical, the distance will be 0, and it's correct. And if it's far apart, with high probability, this will be bigger than epsilon. And of course, if they are close, then, maybe you're lucky, maybe you're unlucky, but you can't guarantee anything. All right? Okay. So now we want to push. So, but this is this is going to be a basic feature that we'll use, even in this non-deterministic case. Okay, so now what do we want to do? Now we want to lift the tester to the regularity words. Okay, so I want to decide now if W n is in R. Okay. So that's explained now in the slides, but maybe I can first go on the first round. First, so I had an example yesterday where I had, say, an expression like 0, 1, 0. Oh, let's call it AB. A, B, A, star, A star, B star. Okay, typically. But then your colleague told me, but you're cheating here because each connected component has 1 state. Okay, which is quite true. If you look at an automata for this regular expression, you will essentially have, say, the state for A star, which will be like this, then the state for B star would be like this. Okay, and then of course you have another state which looks like, you know, A here, then B, and then A, typically. And this behaves like one state somehow, which is true. So in other words, you have only one loop in your connected component. Okay, and it's entirely true that, you know. Okay. Now, if you want to make it more, you know, standard, say, take the star of this. Okay, if you take the star of this, so you're looping the whole thing. Okay, and this time you have a really connected component with many loops. All right, and which is the real case. Okay, and so I don't know if you see, but from this regular expression, I constructed a polytope for the U-stat vectors of the word that are in the regular expression. And this polytope will be exactly the same if I put a star. Okay, so for the edit distance with move. So now let's explain this. So let's assume you have a Wn. So now, of course, let's assume I have indeed a regular expression which corresponds to one connected component. Okay, so one connected component is essentially, you know, it's like a graph where you have many points and you have loops everywhere. Okay, so in a graph like this, the first thing you do is you look at single loops, simple loops, so loops that are the smallest. Okay, and you imagine that any other loop is a combination of simple loops. Now, the key to the story is that if you take here m states, the number of simple loops is exponential in m. Okay? All right. So exponential in m, for what we do, it's not essential because we're not really looking at the complexity of the regular expression. We're looking at an algorithm that decides from W's n's point of view. So what is large is the word, not really the regular expression. But let's take the regular expression into account too. Okay, so let's imagine you have a word like this, and it's, you know, you're trying to make a run. Okay, maybe it's impossible to make a run, first of all. Okay, but if it's impossible, what is still possible is that you imagine you put any states here, and you go as far as you can in the word. Okay, there is certainly one state for which you can go as far as you can, as far as having a run. Maybe you will go all the way, in which case you will have a run, but maybe at some point it's impossible to go further. Okay, and we call this a cut. So at this point, you know you have to do something, you have to edit. Okay, but then you can start right after with any other state. You go as far as you can, and the same thing, you meet a cut. Okay, and so on and so forth. All right, so the question is, you can see that suppose I have very few cuts. If you have very few cuts, then you can correct in the sense that from this state here, which was still a good state, you know there is a path from this other state here. So you can put a small edit. So let's call U, which will be of size less than m. Okay, because there's only a path of length less than m that corrects these two guys. Okay, so you can see that if you have very few cuts, okay, the number of edit operation is proportional to the number of cuts modulo this m. Okay, so therefore if you are far, it means you have many cuts. Okay, that's a key. So if you are far, you have many cuts, and so what happens is that you imagine you have many cuts. Okay, so many means a proportion of n. Okay, so many cuts mean say alpha n number of cuts. Okay, and then what you can do, imagine, is you do the following thing, that let's suppose you take a random subword, then you're looking at what is the probability that when I take a random position, say here, for some k, I find a double cut, so I find 2 cuts here. So if I find 2 cuts, it means that in this space, this subword is certainly infeasible in the sense that it is a witness of the fact that this word is not accepted. Okay, if I find only 1, I don't have a witness, because if I find 1 here, for example, then it's entirely possible that if I start with some state, I go up to there, without meeting the cut, because that cut was generated from a certain position which was dependent from the other guy before. Okay, so I need to find 2. And then you have to make some small computation, is what is the probability that you find 2 like this, and you find it, you will figure out that if you take the length here of the order of say m divided by epsilon, so here you take this, then the probability that you find a double cut is extremely high. So actually you could use this as another tester, which is not based on statistics, but which is only based on whether do I find witnesses for the fact that I'm not in the language. So you could entirely have another tester which does the following thing, is that it makes random position, it tries to find a run, and if it, by putting all possible states here, and you know that if you have a double cut, it's entirely impossible. So you know that if you're epsilon far, you have many double cuts, and therefore the probability that you find 1 is extremely high, and therefore that would be another possible tester. Okay? All right. So now let's imagine what happens when you have a run. Okay, so let's now open the box and imagine what happens when you have a run. So now I'm in between 2 cuts. I have a run. Okay? So, and imagine this, of course this is very long. Then what happens is that you will go through simple loops many times. Okay? Necessarily some loops will occur many times. There's some loops U. So then what you can do is move the U together. So in a sense that if this is W, say, W prime, where you make a move, where you stick here the U, but after that you stick the same U. Okay? Okay, here I'm moving the second U right there. Okay? And I'm making a move, of course, but W prime is close to W, right? But then I can do this for essentially all the simple loops. So I can conclude that I can get a word, W double prime, where I will have, say, a small prefix, a W0, and then I have U1 to the A1, U2 to the A2, UK to the AK, maybe some other W alpha. Okay, so what I'm saying is that I can, with a few moves, so how many moves, that's what we have to figure out, but I can stick all the simple loops together to some power, and you can see that indirectly, if you do this, you're getting close to the statistical version, because these powers give you actually the powers that you observe in the polytope. You remember we had this so if you're looking at this, for example, I introduced, so some vectors, say S1 would be the U stat K of ABA star. And this, by definition, is the limit of ABA to the n, okay? And that's one of the points of my convex hull. So the K, so remember here was S1, and I would do the same thing for S2 and S3. And essentially, what I'm saying is that any word which is close to this language has a u-stat vector which is inside the polytope. And every word which is far has a u-stat vector which is far from the polytope. So this distance should be bigger than epsilon. Okay, and that's my tester. Okay, so why? So see, what happens is that by doing this, you're concentrating on some A1 power of U1. So U1 here would be ABA, for example. And the density on ABA is precisely the density on S1. And if you do the same thing for S2 and S3, so imagine that in terms of density, this is maybe 1/2, and this is 1/4 and 1/4. So you have 1/2 of S1, 1/4 of the other, so you're roughly here. Okay? So you're in the complex with here is 1/2, here is 1/4, 1/4, you're approximately here. Okay? So the key to the story is make sure that when you do this, the number of moves is bounded, okay, by some epsilon n, so you're still close. Okay? And in this world, if two words that are close, they get close statistics, so we know this, and therefore for this distance, it's equivalent to take one word or a close word. It plays exactly the same role. So now what we have to check is exactly the fact that we're not going to be. The number of moves is going to be small here. So I have this explained on the slide. So maybe at this point I can switch to the slides, and then we'll go on from there. Let's see. It's still handy to have a board. Okay, so let's. Okay, and so of course the next step will be how do you build this polytope? Okay, because as we have seen, you may have an exponential number of simple loops. So potentially you have an exponential number of points here. But in actual fact, I'll show you that you only have a polynomial number of points like this. And this is, of course, the key idea of using statistics is that you have to imagine of how many different statistic vectors do you get. And we have to think that you have only a polynomial number of different statistics. So you have exponentially many loops that map into polynomially many statistics. And that's why many of the loops will map to the same vector. Okay? So that's what I want to explain now. All right, so here we are. That's what we're trying to do. So we're trying to do only this, right? The membership tester. Now, once you understand the story, you can do many other things, like, I give you two regular expressions, and I want to know if they're close. Okay? And you can eventually do, so you have to imagine that now, instead of regular expression, you may think of, for example, context-free grammars. Maybe you've seen this in classical automata theory. I give you two context-free grammars, and I ask you if they define the same language. Now, it's an undecidable problem. Okay? Now, if you look in an approximate version here, it's totally decidable, and it's actually very easy. Okay? All right, so here is the argument that I was trying to explain, is that so if a word is close to some language, okay, then it will be close to a word where you stack the simple loops together, okay, and the loops are compatible. Okay, now there is one one trick here that I don't explain is that in actual fact, if you give me the automaton for the connected components, I'm going to compute a to the k, so the automaton that accept sequences of k letters. Okay, so if you have a connected components, then you build the connected components for the k iterations, and that's what that's why you're going to look at. So why do you do this? Well, you do this to minimize the number of moves. Okay, because now remember we're close when the number of moves is smaller than epsilon n. Well, epsilon n is like n over k, right? But by doing a to the k, essentially I'm looking at k letters as one letter. Okay, so therefore I can move essentially all the letters the way I want. Okay, the number of moves will be exactly the number of letters. Okay, so by doing this, of course, you can stick all the basic simple loops together, so you be close to this guy, and therefore you define H to be the convex hull of the U stat of the single loops. Okay, and then so you can show that so you'll have a convex, I mean a complex polytope, but of course you can always say that if you take a point, you can decompose it with only a few of the summons. Okay, this is we call a classical thing in geometry, and therefore it will help you to find exactly if you're looking for a particular decomposition, it will be very helpful. All right, so now what is okay, let me. Okay, so this was also a classical, another way to explain it, and this was done, of course, in the 60s by Rohit Parikh, is that somehow if you are in a language, then you use that vector is in the polytope. Okay, yeah, and that goes back to the classical, you know, automata theory thing. Now, what is new is the fact that when you're far from the language, then you use that vector is far from the polytope. Okay, which is essentially explained in this story. So on this picture, this polytope is a polytope for this regular expression. This polytope is a polytope for this regular expression. And now I assume I have a word, and looking at the statistics by sampling, here is my position, and I know that the edit distance which moved to the language is this, which I can compute by a linear program because of, you know, standard linear algebra. So that's essentially the reason why now I have an extremely simple tester. All I have to look is to compute a vector and its distance to a convex polytope, which is possible if the polytope is not too hard to build. So now the last step is how do you construct this polytope? And this is what we're going to do. That actually H is a polynomial time object that you can build in polynomial time. Okay, so why is that? So here you have a complex stories, but you can imagine that what you do is you enumerate all loops of a certain size, and you may have many. But then you look at the statistics of these loops. So for example, if you think of the loops as blocks, maybe, you know, the big letters are sequences of small letters. So for example, if you're looking at the block ABBA, it has the same statistic than BBAA, right? And actually, the key question is how many different statistic vectors you get. Well, you have to imagine that what's the number of possibilities for the first component? Well, the first component, if it has one occurrence, the density will be 1 over n. If it has n occurrences, the density would be 1, but those there are n possibilities, right? For the second, there are n minus 1 or so on, but even if you imagine that each component has n possibilities, that means that the number of different statistics is n to the dimension of the vector, which is 2 to the k. Okay, this is a rough bound of the number of different statistics vector for a certain k. This is polynomial, and yet the number of simple loops is exponential. Okay, so that explains why H is a polynomial time object, and what you can do is compute it by just matrix iteration. So just imagine you take the adjacency matrix of A to the k, okay, and now you iterate it, you do this matrix to square, cube, up to n, and then that gives you all the, you're going to collect all the simple loops in this matrix, but instead of collecting the simple loops, you collect the statistics of the simple loops. And therefore, instead of growing exponential, you will grow polynomial. Okay, so that's the key. In this matrix multiplication, okay, I imagine that I'm multiplying one step further, so I have the matrix at step t for path of length t. I do one step more of matrix multiplication, but my key components are sets of U-stats. They're not set of simple loops. And I know that I have maximum this number, so therefore matrix multiplication at stage n will collect a polynomial time object, which is my k. Okay, that's why I claim that this is entirely feasible, because even if the graph is totally dense, if the connected component is totally dense, which is the worst case, this will collect you a polynomial size object, and therefore when you're going to look at the distance to this polytope, you have a linear program which is a polynomial size, and you're in business. Okay? Okay, so here is a membership tester explained differently. So first of all, you pre-compute the H. Okay, so H, of course, it depends on epsilon in the sense of K is 1 over epsilon. Okay, so here you build A to the K, then you build the iteration of the matrix. You have it. You sample the word, so you have this vector, and then you look at the distance to H to the epsilon. And here are the complexities. Okay, so key thing here is that the query complexity is like this, which is not too bad. But you still, okay, the problem is that we are still exponential in 1 over epsilon. So this is the key. Think of k is 1 over epsilon, so you're talking about n to the 2 to the 1 over epsilon. Okay, this is actually, okay, so your polynomial, true, but your polynomial with an exponent which is actually exponential in your precision parameters. So, for some people it's actually not so good, but depends what you do. All right, so here's a membership tester. All right, so now just, okay, let me just sketch here basically what's going on. This is also, say, byproduct. You want to say that you want to, test whether two regular expressions are included one in the other. So essentially what you do is that you build a polytope for one, you build a polytope for the other, and you check the inclusion. And one very rough way to check for inclusion is to imagine a grid, okay, and you check all the points of the grid, okay? But there are much smarter way to do it. One smarter way to do it is to make a random walk in one and to check every time if you exit in the other. That would be a much smarter way to do it. Okay, so with this you can do a whole bunch of interesting things, but let's skip this. Now let me give you a similar version for the trees, because actually when we did this work the main motivation was the trees. So you replace regular expression by DTDs and or tree automata, and essentially you have the same result. Okay, So what happens to trees? So for example, let's suppose this is a binary version of your n-rank tree. Okay, so you have a left successor, right successor. And so what happens is that this is a global property of trees. Imagine that you compress for every node, you compress in the label the finite subtree that you see. Okay, so here you're seeing a finite subtree where you compress it in the label. So now you have a much complex, much more complex label like this. Okay, and suppose you do this for some k. So you're going to reduce all small branches, and you're going to keep big branches, right? But big branches now you apply a move. So this guy, you move it there, and it gives you a word. It's like a word in the end. All right, and this is a general phenomena. Take any tree, okay, apply some local compression, then you'll find big branches, and if you move them, stick them together, you're back to a word. So we're back to the previous situation, but of course on a much larger alphabet. So that's one way to understand this, but it's quite correct. Okay? Okay, so infinite words, let's switch to this. And now let's go back to, okay, so now we have the situation where edit distance with moves, we do pretty much everything. All right, so question is, you don't like the moves because in many occasions the moves are, it destroys the structure of the data and in a non-obvious way, which is quite true. So now, how could we generalize the approach to edit distance? Okay, so imagine you have this regular expression, A star, B star. Okay, now two words, this one is in the regular expression, this one is far, right? Because you have to raise B, so it's far for the edit distance, but it's close for the edit distance with moves. Okay, one move corrected. Okay, so obviously, but what we have seen is the U-stat vectors should be close, right? And yet the edit distance is large. Okay, so U-stat as simple as this can't cope for this regular expression and the edit distance, correct? Okay, so now introduce the U-stat square. Okay, so here is the U-stat to the power 1 of dimension 2. Here is a U-stat of power 2 for letters only, because this way I have a dimension 4, which is easy. So first of all, you can, on this example, where does this come from? Here, here's the word. So A, B, 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 I think the word I took yesterday, and I figured we pretty much, I think the example we had only 5 letters. Okay, if I have 6 letters, so this is the density of seeing an A and seeing an A after, 6/21. Okay, and this is the density of seeing an A and seeing a B after. Okay, and of course you can see that seeing a B and seeing an A after, density 0, which is fair. Okay, and yet it will be high in this for this second word. Okay, so you can immediately see that if you're looking at this U-stat vector, it will differentiate these two guys. Okay, so the question is it a general phenomena? And the answer is yes. Okay, so the answer is yes in the following sense. Suppose now you have, so see what happens here, you have a connected component followed by another, right? So take a general automata and decompose it into connected components. Okay, so you would have what is called the graph of connected components, and you can enumerate all the paths in the graph from an initial state to an accepting state. You have finitely many paths, right? Now, what is the depth of this path when you count just the connected components? Well, you could have, for example, component 1, followed by component 3, followed by component 5. Depth 3. Okay? So the depth of a regular expression is actually the length of the longest path in the graph of connected components. Okay? And this depth is going to defines the order of the statistics you want. In other words, the claim is if depth is 17, then you do U stat to the 17. Okay? And then you will essentially have the same thing. Okay? So that's what I want to show. So first of all, you have to think of what happens when you have one single component. When you have one single component, edit distance and edit distance with move coincide. I don't know if you see this, but this comes from the correction that I put here. Okay, so imagine you do a run where you're looking at cuts. Okay, you have one connected component and you're looking at cuts. Starting from some initial state, you have cuts. Okay, and we've seen that to correct, you only add little sequences. You never make moves. Okay, so that's so essentially, if you have a move, so just imagine you have a move in a word, you can simulate it by some edit like this. So this is something important. So let's suppose I have a word and I make a move of that section, put it here. Okay? Well, what you actually can do is edit from that point a little segment that takes you there, follow that segment, and then from that segment put another segment that back here, and then here back there, because you're in a connected component, so from any state you can go to any other state with a little segment of size bounded by m. Okay, so you make a correction of say 4m edit. So one move can be simulated by a constant number of edit operation if you are in a connected component. In the same connected components. Okay? So now, here's the key, is that if you are given a word and a regular expression with p component at the maximum, what you need is to guess where the border is. Okay, so in other words, so let's suppose that, for example, you have three components, so C1, C2, C3. Okay? So by connected components, you see what I mean? You take whatever star, okay, followed by whatever star. Okay? So you have three. Now, if you are given a word, okay, if it's accepted, then there is a way to decompose this is C1, this is C2, this is C3. Okay? Maybe it's only C1. There is no C2, C3. It's possible. Or maybe it's C1. Okay. If it's accepted. Now, if it's not accepted, there could be one cut, for example. So it could entirely possible it's C1, say, and then from here you start and this is C3, which is entirely okay because you can put a little bit, little segments here that connect C1 to C3, and it is of course of bounded length, bounded by the number of states. Okay? So what you're going to look at is all possible decompositions, okay? And then for each connected components, you will apply the basic U-stat construction of order 1, because we're dealing with edit distance with moves. Okay? So all you have to find out is essentially what you see here is in the proper order compared to there, compared to there. Okay? All right. So now here comes an interesting notion, which is a non-deterministic property testing, which is essentially the idea that you can guess. Imagine you guess this position, you guess this position, you guess that position. Now, how do you guess, technically speaking? Well, you guess essentially monadic predicates. It's like putting a color here. You put a color here, a color there, and a color here. You need 3 colors. So you need 3 extra monadic predicates. And now the colored words, okay, if you're looking at the statistics of some order, you can project on the statistic of C1. Okay, so I don't know if you see this, but if I have give you the statistics with an extra color, so it means an extra letter, so you get a huge vector. If I only take the components that are colored by C1 and I normalize, I will get the statistics of C1. Okay, so now technically the Lovash definition is pretty much the following thing, is that you will say that a property is non-deterministically testable. So here will be monadic non-deterministically testable if I can find monadic predicates, okay, such that, so these are monadic predicates, so that the colored words is in a property P prime, which is itself testable, okay, in the classical sense. So P prime must be testable in the classical sense. I guess some coloring, and my solution is only in my property if there exists a coloring such that this is in P prime, okay, which is the most natural thing. Okay, so okay, so that's a key notion, and it's quite surprising that nobody thought about this until about 2 years ago. And Lovash thought it in terms of graphs, so it's exactly the same thing, except because you're dealing with graphs, he allowed here not unary relation but binary relations. So he guessed binary relations so that the whole thing is testable, okay, which is more general, of course. Okay, and the typical example that he gives, so let me give you one of the first motivating examples in the case of graphs. If he takes the following problem, so you're given a graph and you want to decide, here is the property P, is whether the max cut is bigger than C times n squared for some C. So what it means is that you have a big max cut. So you make variations on the max cut problem, which is NP hard. But I given a graph, I ask you, is there a large max cut? Okay? Now, of course, it's NP hard to decide this, but what are you going to guess? So his approach is the following thing. You see, he says, here, the tester is not obvious. I don't see the tester for that. However, if you give me a coloring, so he said, okay, I need to guess the coloring. So in a graph, principle of max cut, essentially, you color one side of the graph in a certain color and the other side by another color, and you're looking at edges like this. Okay, so let's assume you guess this color. Okay, now what you can do is take a random edge, and if you take a random edge with, if this max cut is large, you should see a random edge which is colored, this colored, or the reverse, with high probabilities. If you only see colored edges that are uniform, both points are colored by the same color, it means probably that the max cut is not large. Okay, so, and this is extremely natural. Okay, and there, so here's a tester. Once you have the coloring, the tester is the simplest thing. Take a random edge, see if the nodes are colored here or there or reverse. Okay, so if the colored nodes are not uniform. So if you have a good, essentially if the proportion is essentially C, bigger than C, then it's true, otherwise it's false. And this is correct. So you have a non-deterministic tester. In this case, you are guessing a unary relation, okay? But in general, the way he defines property testing is guessing a binary relation, so a unary relation is a special case. And then he proves that if you are non-deterministically testable, then you're also testable for dense graphs. So it means there is a tester, you know, without guessing. Okay? But finding the tester without guessing is extremely difficult. Okay? And finding the tester with guessing is extremely easy, but then you rely on this big theorem, and that's it. Okay? So here we're in this kind of a similar situation. What is very natural is to guess the position of the connected components. Okay? So in which case, what should be P prime? Okay? Well, P prime should be the property that each part here is close to C. So this part is close to C1, this part is close to C2, this part is close to C3. Okay? And this, I can do it with my previous tester. Okay? Because edit and edit with moves are the same. All right? So, and then now, so all I have to check, you know, is that C2 is after C1 and C3 is after C2. And this I can do with statistics of order 2. Okay, so if you remember the previous example, this example, so, well, just imagine you put C star here. Okay, well, you can imagine that actually statistics of order 2 can check you that the B follow the S and the C follow the B. Okay, so actually in a language where you have different letters for each component, it's exactly like having a guess. You know, you don't need to guess if you know that each, you know, the alphabet of the connected components are disjoint. It's exactly like somebody did the guessing for you. Okay, so in which case you can do the non-deterministic property test. I mean, the tester non-deterministically only needs statistics of order 2. Well, here I put 1, but it should be 2. Okay, it could be 1 if you allow not only the statistics, but you allow some random queries. Because if you have the statistics of order 1 and you can have random queries, then with random queries you can check that C2 follows C1 and C3 follows C2. Okay? But you see, the idea of the approach here is that you want to replace the random queries by some statistics. Okay? And so if you want to do this, so in other words, you don't allow any more random queries, that should be a 2 here. Okay? And now deterministic testers need P if P is the depth of the regular expression. Okay, and then you can show this. I mean, you can show the lower bound. So here, so it's another way of saying the same thing, is that this time, so the U stack 2 is small, is equivalent to the distance, edit distance is small. Okay? Right. Okay, so here if I have 3 components, so for example this, then statistics of order 3 small equivalent to distance small, edit distance. Okay? So here, for example, if I do the statistics of order 3 for length 1, yeah, I have a vector of 56 possibilities, and I computed here AAA. How many AAAs do I have? Well, first of all, you have 1 where they're all identical. Okay? Then 1 where the 2 are there. One, you count them all. I think that I found 7, but it could be okay. Now you see the point. The point is as the power grows, the dimension of this vector grows. Okay, but the number of samples still is of the order of 1/epsilon square, and therefore samples are going to approximate larger and larger vectors. Okay, this is exactly what we gain. Okay, and here you really see the power of randomization. Randomization pays off when you have huge vectors that code a tremendously amount of information, where you can sample it, approximate these huge vectors. Okay, so it will be necessarily sparse, and yet the approximation is good. If you have this situation, then this essentially is a key to the story. Okay. So maybe, let's see, maybe we're going to do a little, okay, so let's make some variations here. Okay, so I never mentioned the fact that some properties are not testable. Okay, because you know, and of course what you'd like is whether a property is, can I find a property that is non-deterministically testable but not deterministically testable? You know, that's the key thing. You know, this is okay, a fundamental story. All right, so now what is the typical situation, the typical example that something is non-deterministically testable is that you're looking at a language which is like this. Okay, let's imagine something like this: U transpose, V transpose. Okay, so you're given 2 words, U and V. And then you want U transpose followed by V transpose. Okay? Now, you see, if I was taking only U transpose, that would be testable. Okay? Because all I do is I take a random point and its symmetric version compared to the middle, and I check if I get 2 letters identical. So U transpose is testable. Okay? Now to get something which is not testable, you have to essentially guess this point. Okay? If you guess this point, then you're in business. Okay? Because if you guess this point, after that you can do the V transpose by the same technique that you do U transpose, but you have to guess the middle. Right? Well, I guess the middle by doing exactly the same thing, right? I guess this component, this color, okay? And then I apply the tester to the first component, then I apply tester to the second component, and is it correct? You see, you have to make sure that the first component is, so there was, here you still have to get, I mean, you have to check that what you color here is to the left of what you color there. This you can do with statistics of order 2. Okay? Because, yeah, I think so. You see, in terms of, if you think of more like an information theory, you need to guess a position. Now, how many bits do you need? You need log n bits here, right? And log n bits, it's actually smaller. How does it compare to the number of bits you need to make a coloring? See, to color, you need 1 bit, but on each position, so you need n bits. Sorry. Okay? So there is a mismatch somehow on the number of bits that you know, if you interpret the guessing by some coloring, or if you interpret the guessing by some position, there is a slight mismatch here. Okay? All right. To guess his position. So with the unary predicates, I'm not so sure that this is quite correct what I said, but what is certain true is that if I can guess with a binary predicate, so if you give me a binary predicate, this is my word, then it's like adding an edge, and you can add the edge exactly to this position I, and here you should see UU transpose, and here you should see VV transpose. Okay, so guessing one position you can do is one edge. Okay, now if I do the coloring here and coloring there, I need to check that my coloring here is to the left, my coloring there is to the right, but then I need extra queries to do it. Okay, but you know, if you don't worry about the extra queries, I think it's okay, quite all right. Okay, so that for this. Okay, so now is okay. Now we can do the trees, or we can do the other properties. Let's do the trees, for example. The trees is not so clear. Actually, so this is a current research at the moment we do. So it's not. So on the website I have notes on that, but you know this is not well written, and so don't. But you know you get the key ideas. All right. So what happens on trees? So we've seen that now trees are quite important if you're a web, you know, if you deal with search engines or so on and so forth, because typically you have DTDs. Okay, you have many DTDs, and you want, for example, to go on the web, and let's imagine you have 100 type DTDs. And you know, essentially I want them far apart from each other in this sense, and then I'm going to go on the web and take every XML file and make it. I'm going to look at the closest DTD. So you know, I interpret, you know, this file or this tree, it's closer to some of these DTDs. Which one? So it's like classifying the web. Okay, and to do this. You sample, okay, and then you make some vector, and you make, and it should work. Whether the question is whether it works with the edit distance. We know it works with the edit distance with moves. Okay, that we know. Okay, the question is, can I do the same thing that I'm doing here on connected components with it for trees? And here comes the key question is that. When you have a tree and you get statistics of order 2 or 3 and so on and so forth, so so for example, if you have 3 trees, T1, T2, T3, okay, so for example this could be connected like this. Okay, so unless you assume that you have some information about the least common ancestor, you're not going to be able to do much. Because if you don't have information about the least common ancestor, essentially you have the basic statistics of order 1. So if you have the basic statistics of order 1, it's totally, I mean, I'm going to show you an example which is equivalent of the A star, B star, where it's not going to be enough for what I want to do. Okay, so you have to assume here that we can have least common ancestors. Of course, if you see an XML tree and you find this, I mean, imagine that you sample this huge tree and you ask yourself, what is the least common ancestor? Well, I don't think you can, on a normal XML tree, it's impossible to do. You have to, if you want to do that, you have to build some label on each node so that you know, you can go back to who is first, who is second, you know, in this sense. Okay? Unless you're building in the XML tree a name that codes, you know, left branch, right branch, and so on and so forth, it's impossible in an XML tree to have this. So here it's just now a theoretical question. Let's suppose we have it. Can I push now the system so that I can have a tester for the edit distance? Now I have more, so I could detail the tester for the edit distance. I sketched the argument, but maybe I could go into the details. We're going to talk about the big data business. I think it's important. I can talk more about trees. Okay, trees, essentially I said, well, okay, let's assume we have the least common ancestors. So we have the statistics. Could the same thing, could we have a tester for the edit distance on trees? This I don't know. Okay, and actually, some days I believe it's true, some days I believe it's not true. The reason why it's much more difficult on tree is the following: is that if you think of the tree, you're given a tree, and you try to put, you know, imagine that your tree automata also have components. C1, C2, C3. Okay, so the initial state that usually you put at the bottom is in C1, and the final state, the accepting state, is in C3. Okay, so at the top you should get some C3, somewhere. Here is C3. Okay, you see, you want to color, you want to partition the tree, so exactly like you partition the words. Okay, so C1 would be at the bottom, and so on and so forth. But then what happened, you don't have a simple picture, because what could happen is that, for example, C3 is almost like here. So like here would be C1, here would be here. Here, this would be C2. But then you could have C1 here, and then C2 here, followed by C1, and then you have C1 here, and then C2 here, followed by C1. In other words, you see what is true is that for every path from the leaf to the root, you have a sequence like this. But what is not true is that you can get to a finite tree. Okay, this because you have an alternation here, C1, C2, C1, C2, C1, C2. So, you know. And this is the difficulty. Okay, see, you cannot default to a finite coloring business. You know, here you have many possibilities, and whether the statistics actually catch this, it's not entirely obvious, and this is the difficulty. So I don't know. I hope within a couple of months we'll have a definite answer to this question, which I think many people are interested in. Now, definitely what is true is that non-deterministically I can do that. Okay, so in other words, if I guess the coloring, then I can make sure that everything's right. So what is quite true is that I have a non-deterministic tester for DTDs checking on trees. Okay, but of course I would like a deterministic one. So. Okay, and this I kind of you know. And now statistics on trees are kind of fascinating, and now what's also fascinating is the business of, for example, if you look at real data, like Twitter data, what happens is that the trees are extremely wide, but not very deep. Okay, so they look like words. In actual fact, approximating the Twitter's data by words on a large alphabet is actually quite all right. And so then we're going to move to this in a minute. So anyway, I haven't detailed too much the original tester. I can do that, but it's kind of going into mathematical details. I'm not sure it's so motivating. So I explained a little bit the problem on the trees. I think one of the big questions is going back to what I said on the distances. So I remember I said, for example, we don't know how to characterize testable properties of the edit distance, and especially compared to Hamming. What is testable on Hamming and what is testable on edit on words are the same properties? This we don't know, and it seems like it's like a fundamental thing to figure out. Okay, all we know is to separate edit with move from edit. Okay, which is already not bad, but all right. And the same questions occur on the trees. Okay, there is a notion of a Hamming distance on trees, which is a notion of, imagine you say, okay, I have a tree, but I only allow edit on the leaves. I don't want to change the structure of the tree. Okay, I can only edit the leaves, but never the structure of the tree. Okay, so that would be like a generalized Hamming on words. And for that, we know that we don't, testing with this distance is usually called a strong edit distance. Now, it can't be done, it's necessarily dependent on the height of the tree. So if you're dependent on the height of the tree, you're depending, you know, in n. So if the tree is not so deep, maybe you're depending logarithmically in n, but if the tree is very deep and you're depending linearly in n, so certainly you're killing this property. Okay, which is not good. So at least we know a few things. Okay? But you see, this area now is the area of okay, reinventing basic automata theory, but in the area where you never read the data. Okay? You never read the data because you can't. Right? And it just happened that in the development of computer science, it's exactly what's happening. You know, you have data, but you can never read them. So, in which way does it match exactly what we want to do in practice? Okay, so that's okay. Let's talk about this. So, if you look at social networks, essentially the way they store data is that they talk about usually NoSQL databases, where essentially they have many servers. I think Twitter is of the order of 10,000, Facebook about the same kind of order. And you know, the data are ordered in some ways. You know, it's not, of course, arbitrary. So you can think of maybe the Russian data would be on one server, the French data on some other. You know, I think it's organized pretty much like this. And now the basic idea now is that communication between servers is expensive. Okay? Local computation is cheap, eventually free, but communication is expensive. So you want to restrict the communication as much as you can. All right? And now comes, so this is a typical example for if you have tried to ask queries to Facebook, for example, or to Twitter. What happens is that some queries are, for example, if you, on Twitter, if you want the current tweets on some hashtags, so you pick the hashtags, and the current flux is free. They give it to you. Okay? Now, if you want the same flux, the same hashtag, but yesterday or months ago, it's a one-shot query. Okay, they give you the answer, but then for 15 minutes you can't ask any more queries. Okay, so in other words, to go to the queries in the time, they need to have a real query to the data. So for them, it costs them something, and they don't want everybody to do this all the time. Otherwise, they'll be totally overloaded with people's requests, and of course, they don't win anything. Okay, so the flux of data is free. But the queries are not free. All right? Now, so I imagine the following game. So imagine I have my servers, and each server has a big word. Okay? And now the game is this. I announce which of the combination, which word I build as a combination of what I've got. So for example, I could ask, well, I want W2 followed by W3. This is my word. Or I can ask, I want W1 followed by, say, W3 reverse followed by W2. Okay? So fix basic combination operators on words. You announce the current data, and you want to ask, essentially, you have hundreds of regular expressions, so you want to ask, well, is my new word, which of the DTD is it closer to? Okay, this is my basic query. All right? Now, of course, if you understood the property testing, well, it's no problem. Then I'm going to get the statistics. Okay? But getting the statistics, why don't you do it once and for all? Okay, in other words, imagine that here we have a basic query operator, and let's imagine you get the statistics from each of the guys here. Okay, so he has UStat of W1, UStat W2, and so on and so forth. And I think it's pretty realistic that once a day he gets an update on the statistics, okay, but not so often, okay, to reduce communications. Okay, so therefore, now you're talking to an agent that has the statistics of W2, statistics of W3, and he should get the statistics of W2.W3. Okay, how can he do this? Now imagine that he also has the sizes. Okay, so he has the relative sizes. Okay, you need the relative sizes of every person. Okay, so maybe W2 is twice as long as W3, so therefore you have a 2/3 density here and 1/3 density there. Okay? Now, I hope you see that if you're on the same alphabet, if you have the UStat of W2, UStat1, say, and the UStat1 of W3, essentially you're going to take the 2/3 UStat W2 plus 1/3 UStat W3, and that will give you the UStat of W. Okay? Now, it's slightly more complicated for the powers. Imagine you have you want the UStat square of W. How do you get it from W2 and W3? Okay, so here you have to think a little bit. So either you get UV in W2, and you get this with probability 2/3 square. Either you get 2 UV in W3, you get this with probability 1/3 square. Or you get one guy here and one guy there, but then all you have to do is to get the UStat1 of W, UStat1 of W3, which you can get from UStat2, and then you interpolate the two. Okay, so the story is, give me any combination, and I can extrapolate the statistics. Okay, what do I do for reverse? Okay, so what do I do for reverse? So imagine you have, so when you see this, you realize that statistics have actually a lot of power. So imagine you do W2 reverse. Okay? So imagine you want UStat, you have UStat K2 of W2. Question, How do you get U-stat2 K of W2 reverse? Okay, well, so this has this is a huge vector, and it has a component U dot U followed by V, right? Now, take U transpose followed by U transpose. Okay, so this coefficient now will be exactly the same coefficient here, but for the word V transpose, U transpose. Okay, you see V transpose. So in other words, you have the U-stat square. You also have it for the complex word. Okay, so in other words, if you have W1, W3 reverse W2, it's no problem. You extrapolate the statistics and you're in business. Okay, so you see the point. The point is, by doing this, I kill the communication. Okay, so I have this huge data. I concentrate on one point which keeps the statistics. I never need to communicate with my data. Okay? So, all right, that's a key point. Okay? All you need to do is once in a while update the statistics, but you can see the statistics is extremely approximate. If this changes a little bit, you know, whatever you do is not going to change much, and so on and so forth. So you're in business. Okay, so in Twitter, for example, in Twitter, we try to do that. So we've been trying to do this in some project, because I have many students, you know, they don't know much about theory, but they know a lot about Twitter. Okay, for them it's game, and whether they do that or some other games is actually pretty much the same. So we're trying to do something. All right. So the question is now Twitter. The question is, you know, it doesn't want to share the data with me. I mean, all these servers with me, right? Otherwise, I would take the statistics on each one, and then. All right. So now, how do I manage? Okay. So the way I manage is I'm going to get, of course, a partial view of this, and what I do is, so I build lists of hashtags. Okay, so I have maybe, so imagine you have so my list is so hashtag, say W, not, let's call it H1, H3. That's my first component. So maybe I have another one, H4, H5, H6. Okay, and I have a set like this. So currently we have a set of size 100. Okay, over roughly 500 words, 500 keywords. Okay, so we have 100 flux. Okay, so what we do now, if we get this flux, we get a constant, you know, stream. So you have a free stream, and some of the on these keywords, sometimes the stream is huge. You know, you have every. If you wait for, say, 1 hour, you have 10,000 tweets, right? Of course, for some of the keywords, on 1 hour, you get 100 tweets. Okay, so it's very dependent on the words. Okay, so the question is, we can't store the whole thing. Okay, and actually, we don't want to store the whole thing because we only want statistics. So our goal is to compute statistics online. Okay, how do you compute statistics online? Okay, you see a stream, you want to do an online computation, and at the end, at any given time on the stream, you want to, you know, say, well, what I've got is an approximation of the statistics. You know, suppose you end the word there. Okay, so is it feasible? So what we do is we fix a number of samples. So imagine M, you fix M, say 1,000. Say, I want 1,000 tuples, and what you need to do is to have them distributed uniformly on your string, whatever the length of the string is. Okay? So can you do that? Right? So, and here's a process. So imagine that, so the strings is coming like you have a first tweet, T1, T2, tac, 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 tac. Then at some point you reach T sub M, the bound, and then you have some T sub M plus 1. Okay? So you can't store the whole thing, so you have to kick one out. So at that point the memory is here. Okay, so you need to choose, do I keep this guy with some probability? And if I do, I have to kick one of these guys with some probabilities. Now kicking one of these guys with probability is easier because I'll do it uniformly. I'll kick with probability 1 over n. Okay, if I decide to have this guy enter, then I get one of those guys randomly with probability 1 over m. Question is, what is the probability I should take for deciding whether I will take T sum m plus 1? In such a way that if I have this process in a continuous way, I will guarantee that my samples will be uniform over my set of tweets I see at any given time. Okay, so anybody has a guess? It's an easy thing to do. So you have to take this guy with probability so if you imagine that this is T sub n, you will take it with probability m over n. Okay, so if this guy is m plus 1, you will keep it with probability m over m plus 1, which is high, it's almost 1. Okay, and then if you decide to take it, then you take randomly one of those guys with probability 1 over m. So you do it now as you ask the same question for T sub n, n being anything. What is the probability to keep it is big M over small n, which is of course the most natural thing, but you can prove now that with high probability the distribution of sample will be uniform. And this is all I need. If I have a distribution of sample which is uniform, then I do my statistics. Okay? So if I have m equals 1,000, p is 5. Usually p is not even 5 for most practical cases, it's usually 3 is fine. Then I'm in business. So that's exactly what I do. Okay? So I have this process where I will keep on each of the flux maximum 1,000 samples per day. So you multiply it by 100, that's 100,000 per day. Okay, so in a month, I have 3 million samples. Well, 3 million samples, if you have a PC with MySQL, you manage this quite well. 3 million samples, peanuts. Okay? Okay, so the question is, what do I do with that? Okay, so first of all, what I can do is enter the business. Well, suppose you want a Twitter on this hashtag 15 days ago, then I could charge you for this, right? I mean, now, you know, Twitter is not going to give it to you, or it will give it to you once, but I'll give it to you, you know, anytime. So I can, you know, I have a competing business. Okay, so now the question, of course, is how do I get interesting analysis, okay, based on my samples, so that I can transform this data into something which is more valuable. Okay, so that's okay. Then we have to play on the R's. What are the R's? Okay. All right, so most people, so you have to imagine, so maybe you used to Twitter, but what do you have in Twitter? You have the content of the message, the ID of the person who sent it, the time, the whole bunch of standard data, but you have essentially the content of the message. And based on the content, people do a lot of things. If you are not familiar, some of my theoretician colleagues in databases, for example, they have a recent paper in the States, in the United States, where they predict the unemployment rate in a state. Okay, you want to predict unemployment rate in some state of the United States? Well, analyze the tweets. It will give you an indicator, and then you compete with indicators computed by economists. Okay, and then we compare the precisions. Okay, so the result is their precision is 10 times better than the one given by economists. Okay, so they took the market of predictions. Okay, in the state of Wisconsin. Okay, so if you're interested in this, the guy who invented this is called Christopher Reed. And he's at Stanford now. He became a Stanford professor with this. Not with this, but many years before.
But they basically analyzed words.
Okay, yes, so which words do they analyze? Well, they analyze what happens if you're in America and you're looking for a job. Well, people realize, especially in states that are not, where you don't have big cities, okay, sort of rural states like Wisconsin is a good example. Essentially, when you're looking for a job, first thing you do is you ask your friend, I'm looking for a job. Because in rural states, 60% of the job people found are through connections. Okay, somebody heard about a job and so on and so forth. So if you're looking for a job, you send a tweet to your followers, say I'm looking for a job, and so on and so forth. And the probability that you find a job through this way is extremely high. So therefore, all you have to look at is how many tweets contain the expression looking for a job, how does it change in time, and you have your indicator. So that's what it does. Okay? But think of many other indicators, especially in big cities, and you have people look for indicators. For example, in Paris, if you know Paris a little bit, you have these metro lines, long metro called RER, but they have delays with extremely high probabilities and so on and so forth. So if you want to ask, well, what is my probability of having a delay and so on and so forth, so is RER working now? People look at Twitter, okay? Because when people are stuck in the trains with their mobile, first thing they say is a tweet, I'm stuck in the train, okay? So just count the number of tweets like this, right? So these are going to be the hashtags, RER, delays, and so on and so forth. So you're going to collect all the data that explain all of this, and then you come up with an indicator, and it turns out your indicator is going to be much more precise than official indicators, for which delays don't exist or whatever. So start playing these games is an intriguing thing. Okay, so it's now all. So I have a student. He doesn't really have a computer science background, but he has an economy background, and for him it makes sense. Okay, the question is how do you valorize, make some value for this, and he has very good ideas, so that's what he does. Okay, so that's a typical example, but I think the interesting thing from a theoretical point of view is that now you have to imagine that the data is the data. What you need is a proper statistics so that you can infer what you want to infer with high probability. It just happened that if you're dealing with edit distance, the U stat to some p is enough. And that's the key. Okay? So that's a typical application, which I think is quite interesting. and it doesn't, you know, it doesn't do much. All it does is this, and the key idea is now to transform a streaming, to have a streaming algorithm that is equivalent to a random sampling. Okay, and this is enough, which is very simple. Okay. There are many connections if you're interested in streaming algorithm. It's a big area currently because people imagine that, for example, you get a graph by edges that are in a stream, okay, and then you want to compute you know, something about the graph. For example, a minimum spanning tree. Okay, so at any given point, you want to update the cost of the minimum spanning tree, and you see edges coming in, but you have a constant memory, so you can't keep all the edges. So it's up to you to do the smart thing about the tree, about the graph. Okay, and you want a minimum spanning tree. So minimum spanning tree, it's totally open whether you can approximate for a general graph. But if you look at one of the last theory conferences, Stark or Fox, I think 3 months ago, some guy proved that if you have the Euclidean minimum spanning tree, so in other words, it means that you assume that the nodes, the distance between nodes follows some Euclidean distance and not the graph distance, then you can do it. Okay, beautiful paper. Okay, so in other words, often you look for the key extra hypothesis to have this streaming algorithm work in pretty much in constant space. Okay, but with a streaming hypothesis. Okay, so of course it gives you it's another way. If you wanted to do a tester for minimum spanning tree, I'm sure you could also view it in that respect, right? But most people now they concentrate on streams. The best example of streams are twitters. Okay, but in twitters, to rely on sample by this process is something extremely simple. You can imagine much more complicated processes where you try to keep you know, some smarter information than just the samples. Okay, here it's a sort of a 0 level of streaming algorithm. You just keep the samples, but at least you know you get something. Okay, so this is what I wanted to say on the application on big data. So it's okay, it's something that is picking up, and I think the dichotomy non-deterministic testability and deterministic testability is going to be important, and the dichotomy with streaming algorithm with a non-deterministic version is also important. So it's also picking up at the moment. Okay, you see, you know, problems like meaning. If I take the minimum spanning tree as an example, so I can do it deterministically if with the Euclidean distance. Maybe I can do it non-deterministically for the non-Euclidean distance. Okay, so that's kind of a, you know, what people are quite fascinated by. Okay, so let's now extrapolate a little bit into this maybe connected areas where we're talking about equivalence. Okay, so that may also interest some of you, because in the case of membership, it's a classical situation where you have some huge data. Okay, and you're only interested, I mean, the complexity is the length of the data. And you don't care too much about the length of the regular expression, okay, or the way you describe the language. Okay, it's not the main parameter. Okay, but now in an equivalence tester, so here's a definition of two languages. What is an equivalence tester for L1 and L2? So it's a given regular expression R1 and R2. So what do you want? You want, if the languages are the same, then you want to accept with probability 1. And if they are not close, you want to reject with high probability. And being close means either one is epsilon close to the other, so it means on a picture that for some distance, the picture is like this. So here is a set of all words. So you have one language like L1, and maybe L2 is like this. Okay, so that would be two closed languages. Okay. Now, if you know some classical complexity, this is a well-studied problem, two regular expressions, and maybe some of you know exactly the complexity status. It's a p-space complete problem. Okay, so the parameter now is the length of R1 plus the length of R2. Okay, this is your data. And to decide this exactly, is so exponential in time, but polynomial space. So it's it's an archetype problem which is difficult. Question is, can you do it efficiently because you relax now the epsilon version? Okay, and so I explained the coherence tester was there. Okay, so here is this picture that comes up, that you follow exactly the same analogy. You build H1, which depends on epsilon. You build H2, which depends on epsilon. And in this picture, they would be far, okay? Because, some point here is far from this guy, okay? But essentially, because the grid, now you can imagine, is the number of points in the grid is exponential in the dimension, true, but it doesn't depend on n, or it doesn't depend on the length of R1 or length of R2. So that's important. Okay, but then you can do something much smarter, and the thing which is much smarter is to do a random walk on the grid. So do a random walk in H1. Okay, and at every stage, check if you're in H2. Okay, now if you have a basic culture on random walk, and I think in Russia everybody knows about random walk. It's considered as a Russian subject. Then you know that so this is now a probabilistic process, but if you have some points sticking out, many points sticking out, you know that you have extremely high probability to reach them. Okay, and you kill the dependency, the exponential dependency on the side of the grid. So that's a key point. Okay, so that's something that people try to apply, but they apply it in the logical sense of model checking. So I don't know if you so model checking is something which is okay. So it includes, then you have to first generalize to infinite words, and for example, the standard thing that people do is that they have a temporal logic formula. Okay, so which essentially would say something like, well, in my language, every time I see an A, maybe I'll see a B later. Okay, and then you want to turn this property, you want to check this property, so we want to check whether my language satisfies this property, and from that from the formula you get a Bussy automata. So you do exactly the same thing, but now you get automata that will consider infinite words. Okay, and think of infinite words, limit of big words as n goes to infinity. So this process is extremely continuous, so therefore you should exactly observe the same thing, and therefore if you have, for example, inputs that do not satisfy the condition, then you will find them with extremely high probability with this. Okay, so this is, if you push this to the area of model checking, it gives you an approximate model checkers, because of course there will be approximation all the time, Okay, if you're close by one letter, for example, I never see that. Okay, you have to be, sorry, if you're wrong by one letter, I'll never see it. You have to be wrong by a certain minimum density, then I'll see it. Okay, but nevertheless, people try to push this in a real condition, which is kind of, well, it's a bit too early to figure out if it will work. Okay, then you can play the game of generalizing to, say, context-free grammars and other logics. So this is a sort of more classical areas where we can play this pretty much the same game. Now let me mention another area which is not on the slide here. So let's finish the slides and then let's switch to this other areas. Okay. Okay, so often the expression is a tolerant tester. So a tolerant tester is a tester like U-stat statistics. In other words, when closed statistics imply closed object. Okay? So that's what we did first, right? Indirectly, it gives you an additive approximation for the edit distance with move. Okay, something I mentioned at the beginning is that computing the exact edit distance with move is NP hard. Okay? And gives you an approximation in constant time. Okay? And of course, you compare with the edit distance, which is polynomial time computable, but impossible to approximate. Okay, so that turns a little bit complexity upside down. Okay, because hard problems become easy and easy problems are hard. Okay, which is a picture which is still behind this business, right? Okay, something which is polynomial time, like edit distance, but you can't get by sampling. Well, that's hard because you can't get the data. So, you know, polynomial time on data you can't read, forget it. Okay? Whereas if you can approximate by sampling, okay, that's fine. That's easy. So it's shifting totally the point of view of, you know, what's easy and what's hard. Okay? So an algorithm which is n square and you can't approximate, that's hard. Okay? An NP hard or p-space complete problem that you can approximate by sampling, that's easy. And there are many. Okay? So that's a key point. All right. So now, well, okay. Essentially, I insisted on the last point. Is so what is, of course, what is the value added by the last point? Okay, the value added by the last point is when you deal with data distributed on many servers. By having the statistics, you kill the communication that would be required if you would do sampling. Okay, and that becomes very important in the current model. All right, so that's all right. So now let's go back to the board and let me mention a few other problems. So one application that has popped up recently is in a slightly different area. So if you go to his webpage, Christopher Ray, you will find a pointer to a YouTube demo. Okay? That's what Americans do, you know. Now every time they have a research project, you need a YouTube demo. Okay, well, you see the experiment explained and so on and so forth, and the interpretation of the experiment. Okay, so computer science is becoming extremely experimental. Okay, and he predicts the unemployment rate. Okay, very impressive. Okay, all right. So one area now, which is pretty new, and maybe you're interested. I mean, you heard about it. is the area of timed automata. So I don't know if it's a big thing in Russia, but you see, so what's the idea of a timed automata? Well, instead of reading letters, say A, B, B, that was our favorite letter word at the beginning, you imagine that you put a time frame. So you read A for 1 unit, the second A you read it for 10 units, the third A you read it for 3 units, for first B you read for 2 units, and the second B you read it for 5 units. Okay? Now, of course, people start with units of times, but they want soon to go to rational. Okay, so maybe it's 1 millisecond, this is 3.5 milliseconds, and so on and so forth. Okay, and there is a notion of a timed automata where essentially on the transition you have constraint on these variables, linear combination of these variables. Okay, and that's much closer to the way people design circuits. If you design controllers in practice, you read some input for some time and it has to be less than something, otherwise some disaster happens. Then you read another signal for another period of time, but you have time frames that are very important. Okay? So I don't want to go into the details of the automaton, but you can imagine that, now imagine that this word is not accepted by a timed automaton. Okay, so I don't want to go too much into the detail of this. So it's not accepted. All right, now let's play edit distance. Okay, maybe by introducing maybe introducing a B for 1 here, would make it accepted. Okay, or maybe changing the 5 into a 6, make it accepted, right? So obviously now you want to generalize the edit distance with cost. Okay? So this would cost 1, and if you kill this guy, it would cost 5. Right? Okay, so you adjust now the cost by the values of the time. Okay? And then you keep everything the same. You're close if the sum of the adjustment relativized to the sum here is less than epsilon. Okay, so of course it has to be, you have to make sure it's still a distance. So one way I look at it is that I say, well, the distance between 2 words, well, I take the minimum number of edit operation and I look at it as a vector with here is a number of edit, and here is the time, the sum of the time. So for example, let's suppose I put B1 here and I erase this guy. Okay, so that would be 2 and that would be 6. Okay, in an absolute value. Okay? But you can see that there is a slight difficulties because now if you want a relativized value, here you want to divide by the length, traditionally, but now you want to relativize by the sum of the time, okay, which is, I don't know, you have to make the sum of the time, right? But then if you're not careful, this is not going to, so if you want to divide uniformly here, this function is not going to satisfy the triangle inequality because of you can have weird things that happen on the time and on the edit operations, but there is a way to normalize it somehow, and this is okay, there is a way to normalize it. Say, imagine that you divide this by the length, the n, and you divide by the sum of the t, but then you make some, this is an approximate distance. All right, and now of course question is how do we get a tester? So I give you a big word, right? And now I want to know if it's in my language. And now I sample. Okay. First of all, can I just sample and decide with high probabilities? All right. So that becomes slightly more difficult. But essentially, the idea, and the answer is yes, you can do it. But then there is a major. So that would be a way to generalize the U stat. So imagine you do the U stat K, say of 1. So this is a time word. So let's call it W. So it's okay. Okay. So T is the sum of the TI. Okay. So obviously, when you take a sample, you see a subword. Okay. So for example, if I sample in this position, I'll see AB. Okay. So my sample will be A3, B2. Okay. And fundamentally, what do I have to do? I have to look at all possible states of my timed automata and figure out, would I have a local run of size 2? And to have a local run, essentially on the time automata, you have constraints on the time. So for example, you could have, for some state, say you would read an A, and the time, usually they call the counter X, would be less than 4. Okay, so you would go from Q1 to Q2. And this is a clock. And usually you may have several clocks. Okay, so if you just look at 3 is smaller than 4, so it's fine, you can do it. If you had 5 here, then you couldn't do it. Okay? So from the time automata, you get a whole bunch of formulas that gives you what's going on. Okay? So essentially, here you have to imagine that you get AB, and then you have some formulas phi 1, phi 2, phi sub k, that give you all possible constraints on the time variables that are here to have a run. Okay? But this number of formulas is finite. Okay, so that the U stat vectors now is going to be a product of the word followed by the time constraints. Okay? And it could be that some of these formulas could be non-exclusive. I mean, you have maybe some formulas that are it could be that this instance satisfies phi 1 and phi 2, but not phi 3, for example. Okay, so that's exactly what you're going to store. Okay, you know that when you see AB, you have to figure out what's going on with this. Okay, so see which one you satisfy, which one you don't satisfy, and this is what you're going to get on the proper statistic vectors. It's still a finite object, much larger, and now you have to prove that nevertheless, if you have the statistics vectors to some power, because the time automata, and this is true, that very often they have connected components. Okay, first you pass this process, and then you pass this process, and you pass this process, and so on and so forth. So you really have connected components. So in that case, you need statistics of some order. Okay, and then you collect all the formulas constraints, and you generalize the statistic vectors, and then the theory generalizes in the sense that yes, if you're close, then first of all, if you're far, I can decide by sampling. If you're in the language, everything will be fine. And if you're close, what I can do is I can correct. Okay, so here, usually what people are interested in is not so much, well, they like the tester, but they also like what comes with the tester is a corrector when you are epsilon close. Okay, so it's something that I eventually mentioned with the cut. Remember when I was looking at the word, putting the cuts and then correcting. And I said, if you're close, you have very few cuts, so the correction will guarantee that the number of edit operation is less than epsilon n. Okay, so in that sense, you'll have exactly the same thing, and it turns out that people actually, having the corrector is very important. Okay, because you can imagine that now instead of integers here, imagine rational values. So you have a rational value, say 2.7, and they tell you, look, if you replace 2.7 by 2.68, then it's fine. Okay, all right. So it's extremely useful. Okay, and then in that context, people really like the equivalence tester. So typically what they want to do is they have a timed automata A. They have a whole bunch of formulas usually in LTL, but they generalize LTL to handle the time constraints. So they have intervals constraints. Well, usually it's actually called MTL sub I. Okay, whatever. They take formulas in some logic, and they want to figure out, well, show me that whatever run I have, it will satisfy the constraints. So I make sure that everything's fine. Okay, and this time there are time constraints. Okay, so this turns out to have an extremely valuable use for people designing circuits, designing components, and so on and so forth, because automatically they can do some model checking, but within an epsilon fraction. And if you understand the tools, of course, you have epsilon going to 0 and see what's going on, right? If epsilon goes to 0, then you go to the real thing. But of course, what happens now is your dependency in epsilon of this kind, in which case it's nice, but very often, unfortunately, it's like this. So if the dependency on epsilon is like this, and epsilon goes to 0, then you're not going to go very, very far. Okay, so if you go into these areas, people really study how to make it like this. Okay, so here the normalization can be helpful, and so on and so forth. Okay, now this is interesting. So you can also think of this Wn as weighted words, which it is. And there is a connection between testers on trees and weighted words. So now let me finish on this to really show you how everything is connected. So why is the connection between weighted words and trees? Okay, so imagine you're searching for a tester on ranked trees. Okay, so imagine you have A, B, A, B, but then I have a subtree here, I have a subtree like this. Okay, so that could be the situation, right? Here's your tree. Okay, and then if you know about DTDs, so the DTD is going to check whether this word AABB satisfy a rule with the predecessor, which is an A. Okay, so it's looking at this neighborhood, see if it's okay. All right, if it's not okay, it has to edit. Okay, now for example, if it's not okay, and imagine you have to change this, right? If you deal with a strong edit distance, it means that you have to erase this whole thing and to rebuild it, essentially. Okay, so it will take a time proportional to the size of the tree. Okay, so then it makes total sense to say, well, let's suppose this size is 10, this size is 20, this size is 3, this size is 5. So that amounts to saying that you are dealing with the weighted words A10, A3, B20, B5. Okay, because every time you edit here, it costs 20. Every time you edit here, it costs 3. All right. So if you deal with a strong edit distance on trees, indirectly, it's exactly like having weighted words for the weighted edit distance like you have in timed automata. So there is a connection between the notion of weighted words and the connection of trees when you take into account the size of subtrees. Okay, so anyway, that's here it makes sense, of course, when the values are integers and big. And the timed automata, it makes more sense when the values are small and you're looking at really the precisions. Okay, whether you have 3.001 or 3.002, you know, it could make a difference. Okay, so if, for example, even this iPad, sometimes it blocks. Okay, so sometimes I read web pages and it really blocks. Okay, so it blocks. It means that I have a word with, you know, a huge factor here. Okay, because it blocks, say, for 10 seconds, and then it goes. Okay, so I read you know, an article. It blocks for 10 seconds, and then it goes. Okay, so in other words, you know, my valid instance is like having a huge value here, and I really don't like it. Right? So you want to kill this, and how do you test this in advance? Right? So, for example, for browsers, it's a very useful thing, and actually, I know that Google does it for Chrome. Is that before they have a new version of Chrome, they make sure through a whole bunch of model checkers that this is going to pass, this is not going to block in this situation, this is not going to block in that situation, and so on and so forth, because of course customers don't like it, right? If you take, for example, Internet Explorer, which is an old version with current HTML file, the probability that it blocks, the probability that something happened is growing every day. Right, as you know, right? And it kills the browser. But this, so before you get you know, the model checking is extremely useful here. Okay, not even mentioning the internet connections, because the internet connections, it turned out it took me an hour to connect it manually when I was at this hotel. And anyway, it was a fun exercise, but it took me an hour. And it's also connected to you know, how long does it take to correct something? Okay. So correctors actually are kind of, you know, they're already used if you know, for example, in HTML, if you forget some, you know, some of the signs, I mean, some of the, what they call it, you know, tags. So, you know, for example, typically you may open your file like this, but you may forget to close it. Okay, most people don't do it. Right? So you don't, some people put this, but they never put this. So technically speaking, it's not correct, right? But the browser doesn't care. Right? So in other words, take an HTML file, randomly erase some of the tags, and see how long it is robust for. Okay, it could be that you raise one tag, everything collapses. Usually not. And the interesting thing is that if you take modern browser, you can erase 10% of the tags and it still works relatively well. But over 20%, it starts crashing. So there is some error correction in there. Okay, so error correction was always something useful and done. It's actually something we do, for example, in some of the classes where I give a file and I ask my students, okay, now make the smallest number of errors so that it crashes. Okay? And the question is how many? Okay, which is reasonably, but some students they like playing with this, which is not too far from playing with the other concept. Okay, so let's go back to what we did. Okay, I tried to convince you that verification is a very standard notion, but approximation is not. Approximation has various formulations. This is one, this is another one, and this is the third one. Okay? This, of course, it serves theoretical purposes. This one, of course, serves a lot of theoretical purposes on the approximation of algorithms, showing that this is hard and so on and so forth. So, typically, I'm sure you heard about it. And now this property testing is trying to import these ideas, but in a very practical sense. Okay, so it closes the gap, say, between theory and practice. Okay, now there are many open problems. So I mentioned a few. For example, characterize the testable properties for the edit distance on words. Nobody knows. Is something testable for the edit distance? Is it testable for the Hamming distance? Nobody knows. Same for trees. So, okay, you have this notion which is very recent, and I think it's very nice. You can actually make a hierarchy. You could have a property which is non-deterministically testable. Okay, and nobody has done this yet, so you could build a polynomial hierarchy by alternation. You could now you could take ideas with the epsilon distance from property testing and inject it there, because see, in the interactive proofs you want to decide there is no approximation, there is no epsilon. Okay, so if it's good, you have to accept. If it's not good, you have to reject with high probability. Well, imagine you replace in an interactive proof if it's far from being correct, then I reject with high probability. So it's the weaker notion. Okay, which you import here a notion from property testing, and it's never been done. I've never seen a paper like this. Okay, and for example, if you take this weaker notion, the idea would be to gain in a number of rounds. Okay, so maybe you have a protocol with n rounds. Now you take the weaker notion and you have 2 rounds. Okay, that's a typical thing that people would do. Okay, now the other, I think, key idea here is don't hesitate to introduce approximation. Okay, so if you have your favorite problem, think about what would be the approximate version of that problem. Okay, not because it's maybe it's totally artificial, but it will certainly bring some light on the real problem itself. Okay, and so that's, I think, the one key idea they should remember. Okay, so thank you, and maybe I'll be if you have ideas on this, don't hesitate to send me email, and the website details, has all the documents. So if you want to study this further, then you have all on the web. Okay, thank you.